Hello.
फिर उनको भी स्क्रीन में लाना है। वो कहाँ से स्क्रीन में आएंगे? इससे नहीं नहीं, वेट दैट शी हैव टू स्टैंड यहाँ पे कहीं भी करने। ठीक। हेलो। Okay, so it's actually we are beyond 4 p.m. So first of all, thank you for joining us, both from the YouTube live audience as well as those who are joining us from the Zoom. And of course, people who have joined us here in the AG66 lecture theater. We've almost forgotten that that is the audience we always cater to. But because this is in hybrid mode, you always have to ensure that people can listen to you in the online system as well. Okay, so I welcome all of you again for this edition of the NSF Wednesday Colloquium. And we have a visitor after a long time physically visiting us for this colloquium series, and that is Professor Kasturi Saha from IIT Bombay, Electrical Engineering Department. But before I formally introduce Kasturi, I just wanted to again reintroduce the NSF Wednesday Colloquium series for those who are joining us for the first time. The NSF Colloquium series, Wednesday Colloquium series was formally conceived by Professor Homi Bhabha, our founding director, who actually would come for one day in the week and meet all the faculty members for lunch, where the colloquium speaker is actually formally hosted as a guest. He would ensure that all the faculty members gather under one roof, at least from physics, chemistry, and biology, and listen to the guest speakers lecture together. And the tradition is such that not only the faculty members, but also the students across the institutes in the natural sciences faculty, they gather and listen to these series of talks. And what has done over the years, what this has done is they have made at least the student training much more broader, that even if you're a chemist, you're going to listen to a biology colloquium or a physics colloquium. And that has enabled not only from the perspective of training, but also across board departmental collaborations, as well as ideas that can be generated. So this has been a very fruitful series for all of us, and I'm lucky to host this for last few years. I just wanted to give a brief introduction to Professor Kasturi Saha. So Professor Kasturi Saha joined IIT Bombay as an assistant professor in December 2016. She did her PhD in quantum and nonlinear photonics group with Professor Alex Gaeta in the School of Applied Engineering Physics at Cornell. Her thesis work involved characterization, time domain analysis, and stabilization of frequency combs generated in silicon nitride micro ring resonators and ultra low power nonlinear optics in photonic bandgap filters, fibers. So the photonic bandgap fibers and these frequency combs clearly, as sort of trained her as an optics person in terms of getting her training from Cornell. Then she moved on to Professor Paolo Capellaro in MIT, where she actually sort of started doing things with magnetic centers. And this is where she worked on a quantum spin-based gyroscope using nitrogen vacancy centers in diamond. Something that she has carried home here in her research work. And actually, she will talk about some of these very nice ideas in the context of this colloquium as well. She joined, of course, she has been in IIT Bombay for almost 5 years now, and she has been doing some wonderful work. She is the DST Inspired Fellow, as well as one of the IIT Bombay faculty fellows. Kasturi was also part of sort of the writing of the quantum materials big project group that DST had put together, and I think Vijay is here as well, one of these members. So this is also a focus for the government to sort of put things together in condensed matter physics, chemistry, material sciences, to bring people together from various disciplines and have this specific quantum materials research that can be sort of done in India. So Kasturi is one of the members of that unit as well. So Kasturi, I welcome you for this colloquium, and we are looking forward to it.
Thank you very much. So thank you for this. No, it's okay. Am I audible now clearly? Yes. Okay. So thank you once again, and just to tell you, all of you, that this is the first talk that I'm giving physically after 2.5 years almost. And if you can't read a small font, something that I've sort of forgotten how it looks like when it's in a big screen, and if somebody's sitting right at the back, please raise your hand and or shout out loud and let me know whether you're not able to see something. So today I'm going to tell you about the work that we've been doing at IIT Bombay, building this quantum diamond microscope for imaging microscopic magnetic fields with NV centers in diamond. So many of you would have heard about this new buzz about quantum sensing and metrology. Just to sort of bring it into perspective, quantum sensing and metrology exists and has been existing for quite some time, and in real life technologies. In fact, we use it for these kind of applications like PET. It's a way of detecting cancer, and it actually uses a quantum technology, and also OCT also uses some of these. If you want to do a very high-end OCT, you can actually want to use photons of very low power so that you don't actually destroy your retina. So you use entangled photons to do some of these measurements. There are two other technologies that are available. For instance, the MRI machine that you are all familiar, it exists in most diagnostic centers. This is the this is the strontium atom atomic clock. This is something that we use all the time for our GPSs, for maintaining the time standards of the world. And then, sorry, please continue. And then there is LIGO, right? These are all quantum technologies. While some of them are primarily for fundamental, sort of curiosity and experiment, the others are real life technologies that we already use. So towards the domain of miniaturized quantum sensing, there are two aspects, two examples that I like to highlight a lot. This is a miniature atomic cardiac magnetic field sensor, and this was built by NIST in USA, which essentially is actually an atomic vapor based sensor, magnetic field sensor, and it senses the magnetic signature of cardiac muscles. Okay, so it's another way of looking at the functioning of your heart and whether it's functioning well or not. And so picking up, instead of picking up the electrical signatures, they pick up the magnetic signatures. And this is a miniature cardiac sensor which is based on an atomic vapor based system. A similar counterpart to this sort of a sensor is an NV center based system, and this is what I'm going to tell you about today, which is a solid state based system. So instead of having a gaseous vapor environment, you basically have atoms or pseudo atoms sort of sitting in a solid state matrix, so that you don't have to deal with atoms flying around everywhere, and you build a sensor which is basically a one unit or one chip system. And NV centers have shown that they can be used as solid state based magnetic field sensors. Of course, I'll tell you more in detail about these sensors, but one example which came up from MIT is where they built a chip scale device out of this NV center. An application of such a sensor would be like if you have a protein molecule next to the spins in this system, you can actually look into the interaction between the spin interactions and understand the protein structure. And this is one of the applications with which the entire field actually started off with, where you want to look at a single spin interact with, or electronic or nuclear spin interact with another, nuclear spin of a molecule and understand the protein structure. And this is something was one of the holy grail sort of a problem that people worked with NV centers. Of course, NV centers have now diverged into various different domains and have applications in, different kind of quantum computing, as well as, other communications, etc. So today in my talk, I will tell you about color defects in diamond, especially these NV centers, and there are, mind you, many other types of color defects. Applications of NV centers for quantum sensing, what are the different kinds of, and this is since I'm dealing with a very wide audience today, so I want to show you what is, how diverse the ranges of these applications are, and then the specific work that I am interested in and why I started looking into these NV centers for looking into wide field imaging and what is its application. So to start off, we have to first figure out what this NV center is. It's nothing but, a nitrogen atom. So N stands for nitrogen. Nitrogen atom, which has substituted a carbon atom in the diamond matrix, and you have a vacancy next to it. And on top of that, this NV together collect an extra additional electron from the lattice of diamond and forms this complex, which is called an NV minus. It's a charge state, NV minus charge state, and that is the NV minus, or the NV of interest, which is the color defect of interest for us. So essentially what happens is that in diamond, which is usually what you're used to, accustomed to seeing, is the very nice and pretty looking, cut stone, gemstone diamond. But when you have defective diamonds, and in fact defective diamonds meaning when you have substitutional nitrogen, or you may have boron or any other sort of material, this diamond becomes a more colorful diamond. And so depending on the substitutional atom, you may have a different color. So for instance, nitrogen actually gives you, if you have a diamond which is with a lot of nitrogen in it, it gives you this bright yellow color. And so if you go to a gemstone store, they'll just tell you that, this is the very expensive diamond, but in actual reality, this is very easy to get because nitrogen is abundant in the air, and so it will always naturally seep into a naturally grown diamond. And so you always, in more often than not, then actually the white diamonds, you actually get yellow diamonds. So similarly, you have blue diamonds as well. Now in a lab, these don't look like this, it actually looks like this, it looks almost like a colored glass. However, we are more interested in these white ones which have a certain amount of concentration that don't give you this kind of a color, but have enough number of NV centers so that you can actually make a sensor out of it. So typically the ones that have NV minus are actually pink, because they emit fluorescence in the red region, so they are about pink and not yellow in color. So what are some of the properties of these NV centers, and why are we so interested in these NV centers? The idea of using an NV center is, of course, first of all, it's a solid state system. And the second most critical thing is that it's a room temperature system where you use optics to probe the system, but you also get spin information out of it. Okay?
Can I ask a question?
Yeah.
Go back. Yeah, so in this case, you have in the picture the nitrogen is tetra coordinated, is that correct?
Yes, there are 4 arms. Yeah.
So then the nitrogen will have a positive charge associated with it.
Yes.
And
so there's a vacancy here. So there's one net electron plus another electron. So there's a spin triplet. Yeah.
Spin triplet. Okay.
Yeah. Yeah, I'll tell you about the electronic structure. Yeah, so the two main things essentially is that one is that you can excite with a green fluorescent light, which is this 532 nanometer light. And then what you collect is a red fluorescence. So in fact, this is a diamond in my lab where we have green laser shining on it, which is focused in this bright spot that you see. And you can see all the very nice orange or red color actually emitting from this, from the sides of the diamond. In fact, fact, because diamond is a very highly refractive index material, so the light actually gets trapped inside the diamond and comes out very nicely from the sides of the diamond. Of course, you also have fluorescence emitted in all 4 pi, and so if you have an objective, you can always collect out the fluorescence from that objective from this focal spot. This is 532 is the green.
532. So that's the gap, energy gap in the NV.
Yes, I'll just come. This is the, yeah. So this is the actual electronic structure. So what happens is, if you have a 532 nanometer laser, it emits 638 nanometer fluorescence light, and of course it's a broadband fluorescence, so you get almost light up to 800 nanometers. But we are interested in the 637 or 638 because that's the zero phonon line. Now the NV center, as you can see, this is the optical ground state and this is the optical excited state, but this is the spin, the spin ground is here, so it's a spin triplet system like I mentioned here. So you have a degenerated plus minus 1 level, and you have a zero state which is split by the zero field energy, which is 2.87 gigahertz here. So what happens is that what is unique and interesting about this system is that you have fluorescence which is dependent on the spin states, and that is why we can read the spin states optically. So the fluorescence that, if suppose an NV were to start off from one of these two plus or minus 1 levels, is essentially almost 30% lower than if it were to start off from this 0, and that's primarily because there is a metastable state here, and so essentially the NV can often transition into this metastable state and then polarize down to the ground state. So you can also optically polarize this system, so you have a very nice way of just shining the green laser at the nano diamond or any of the diamond, and you can just polarize the spins into zero state, pure zero state at room temperature. So it's a room temperature system you can control with a microwave and RF, because you have the microwave level. This is microwave domain essentially, so this is 2.87. So you can control this system, so it's a 0 plus minus 1, so you can go either 0 plus or 0 minus and use those two level systems. And then, so if you now think of the spin properties and the qubit properties, so one of the things that you want to analyze is essentially the coherence time of the system, or how long is your qubit good for, right? So one of the things, if you have an ensemble, then this ensemble means if you have many spins, so if you have many spins together, then this coherence is about, T2 star is about 1 microsecond. Really a very good sample will have about 1 microsecond. A single qubit, of course, will have T2 stars of about 500 microsecond. Of course, any dynamical decoupling sequence is applicable here, so you can extend it. Yes?
Just wondering if somebody made a laser out of this?
People are trying to make masers out of it.
I mean, what I mean is that you have the state, which is metastable. So it's typically like Ruby, you have 3-level systems. Somebody tried?
No.
I'm not aware of.
No, not. Yeah, so it doesn't work out very well for a laser, but it works out for a maser pretty well. So people are trying to make a maser out of it. Yeah, so what we can do is polarize to the ground state, and of course this NV center is also a fairly complex system, because you have nitrogen 15 and nitrogen 14, and of course carbon 13, etc. So it's a fairly complicated system. So if what happens when you have
you go for single qubits, right? Single NV centers. So I'm just following up on Ravi's question. So that for your interest, I understand why that interest is. But suppose you have high density of these things, which can be created, right?
Yeah,
so then in principle, there should be lasers. If economically they may not be appropriate, but there should be lasing possible.
Yes, lasing is possible, but it's
I guess you guys are going for single cube.
Yeah, I mean, you can go either ways, but people want to use the spin properties for the sensing, because that is more of the, that's the application domain that people want to use it for. Yeah, so if you apply a magnetic field, this traditional Zeeman effect takes place, and so what you can see is that these plus minus 1 levels will split. Now you have a pseudo 2-level system. So essentially you can drive these 2 levels, or you have control over these 2 levels. And what you see in an actual measurement is that first of all, we start off, if you polarize, you start off at 0. So if you measure the fluorescence, let's say it's some X amount on this fluorescence curve, and what happens is that when you start driving and you apply some microwave that is resonant with this with these 2 levels, you will see a dip. And that's exactly shows that at that frequency you are on resonance with this level. Similarly, you will have another level which is on resonance with a -1 structure. Now, when you change this magnetic field, this line will shift. That's because this is a very well calibrated, naturally calibrated system, because gamma or omega is essentially gamma B. So that means that if you have gamma, which is a very well-known number here, 2.8 megahertz per Gauss, so it will just shift with an applied magnetic field. So any applied magnetic field will move these lines and you can measure the fluorescence. So essentially, if you want to measure a magnetic field, all you have to do is apply some, bias field, quantize the system, very well calibrated system, and then you can apply an additional field and you measure that additional field.
It's like the microwave is a control laser. Is that
yeah, the microwave is an additional.
I mean, it's like depending on what I do with it, I can switch.
Yes, you can always. This is my control.
So 2.87 megahertz. How precise? I mean, what kind of, when you talk magnetic fields, how much is the shift you'll get? By
this is the shift, 2.8 megahertz per Gauss.
2.8 megahertz
per Gauss. That's the shift that we can get. That is what we can measure. But we can have much higher sensitivity. I'll just come to that. Yeah. So
this is just sorry.
Yeah,
this is just essentially free electron sensitivity in some sense.
Yes,
right?
Exactly.
2.87 gigahertz per Gauss is a free electron sensitivity.
Exactly.
My question here is, don't you see hyperfine? That is what I think you are showing.
That is exactly.
So because you're at a single resonance.
Yes.
So with a nitrogen 15, you will have
N14 and N15, you will have the corresponding hyperfine levels. So if you have, if you have the, if your sensor is a good enough sensor and it is not broadened by all sorts of things, you will
start seeing this.
Okay. Yeah, and I will show you measured data for hyperfine levels.
And you can use fluorescence to detect the hyperfine also.
Yes, this is fluorescence.
Okay.
This is fluorescence.
The local environment of this vacancy, how much does that perturb?
Oh, that depends on the system. You can.
In a practical system.
Okay, so when we apply a bias magnetic field, it depends on the stability of the magnetic field. So it depends on, whether some, 1/10 of a Gauss, if it fluctuates.
No, I'm not talking about the applied. I'm talking about you create this center.
Yes.
But then there are.
Like other external, like nitrogen or carbon-13.
Yes, exactly.
Yes, so that is what ultimately decides the coherence time, and that essentially takes care of all the environmental fluctuation, and it tells you that in spite of all these fluctuations, this is about 1 microsecond you'll get, or maybe 500 nanoseconds to 1 microsecond in an ensemble. Now, exactly which one is what is fluctuating, that is something that you have to do depending on the sample.
But that should depend on the doping density, right? Of the
doping, yes, there is a huge amount of calibration on doping density. It depends on the environmental strain. So how the diamond is grown, those things all matter. So everything matters. Yes, so if you actually look at the Hamiltonian of the NV center, it is actually sensitive to both magnetic field, electric field strain and temperature. So you see that you have a method by which you can couple any of these, fluctuations into the system. And it turns out that at least 2 of them you can do simultaneously. And what people have been doing in this recent past is actually to look at magnetic field and temperature simultaneously in many of these systems. And as you can see, because this is a very nice and complicated system, you have a lot more lines to work with, and you can really, cancel out noise by doing, common mode sort of measurement. What is beautiful about this system is that it's a vector magnetometer, okay? Because you have not just, so there are 4 classes of NV centers. So the nitrogen can be in any of the 4 arms of this. And so what happens is that you have all 4 lines of about the 2.87 gigahertz, and so that means that you can now do all sorts of, you have several omegas to work with to get whatever fluctuation that you want to measure, right? So that is, and so essentially you have much more information than you need to reconstruct back a vector magnetic field. Okay.
Just the previous slide, just remind me again, I used to know this, the 4 orientations automatically give you different mean frequencies just because of their alignment with the magnetic field?
No, because of the lattice.
Because of the lattice.
Yes, because of this, because you see the red dots
are... So the zero field splitting is different for the 4
No, the zero field splitting is 2.87.
Okay.
But the projection now, so suppose the B field is at some random orientation, it will see different projections in different.
So it is the field's projection.
Yes, it is the field's projection that it will see. Yeah.
Okay.
So that's why you see 4 on this side and 4 on the other side.
Okay. Yeah. Thanks. Yeah.
Yeah, so in a nutshell, now what happens is that if you go back and do all these measurements, you'll see that if you have those 4 lines, depending on whether you apply magnetic field, temperature, electric field, strain, etc., the lines move in a different way. And that is what allows you to measure all these different properties of the NV centers. Okay, so that's the, and I would, if you're interested, I recommend this Journal of Applied Physics review that came out very recently that talks a great deal about NV centers for magnetic or for all sorts of sensing. Now, what is finally this microscope? So it's a NV center. You have some magnetic field sample. You shine green light. You collect the red light. The red light has all sorts of information in it, and you excite with microwave so that you can control your NV centers. You get all that information. Any local perturbation near the NV center will be reflected on the same red light that is emitted in fluorescence. And so that gives us a spatial map of any sort of magnetic field feature that is present in the nearby vicinity of this NV center. Okay, so to give you sort of dimensions of these numbers, DC sensitivity is about 50 picotesla per square root hertz. Now, with ferrite concentrators, these are some flux concentrators which basically sort of concentrate the magnetic field. You can even push it down to 0.9 picotesla. AC sensitivity, which means if you have a fluctuating magnetic field around this whatever bias magnetic field that you have applied, you can use different kinds of schemes, pulse sequences, and the best AC sensitivity reported is about 0.9 picotesla per square root hertz. Now, because I'm talking about a magnetic field imager, we have to talk about spatial resolution. Here we are diffraction limited because you are using optics. This is a 532 nanometer light, so it's 250 nanometers is approximately what we have. Then this is with optically enhanced techniques. Of course, this is the purest from the first 0th order microscope. You can always build higher order microscopes, and you can really push it down to at least 5 nanometers. And what is beautiful about this is that you can also do. Yes, 400.
When you say optically enhanced techniques, you're talking about statistical super resolution?
Yes, super resolution.
Yes, get statistics.
Yes.
Then your NV centers have to be far enough apart.
That is true. You can also do STED. Yes, you can also do STED, where you can also use a donut beam. So you can do that also. That is also possible. Yeah. Okay, so this is the basic sort of imager that we wanted to build, and we wanted to see what can we do with this, right? So what are the things that people have done, and what can you gain out of using this sort of a sensor? So indeed, spins are naturally quantum, and so what you can do is, if you have a lot of spin sensors, you get a square root n advantage of your sensitivity. Now you can use different kind of techniques, for instance, use cavities, etc. You can push it up and really go to the Heisenberg limit, where you can scale it with n, right? And this is something that
you can also use this as a we'll discuss this as a tip, for magnetic force microscopy.
Absolutely, you can have it as so you can have a single NV center on an AFM tip, and you can scan it, and that is possible. But we are talking about wide field.
Of course.
Yes. Right. Okay. So what have people really focused on? People have looked at superconducting samples, so you can actually see vortices, for instance, in wide field, and that's something that is different from the traditional way of looking at vortices. People have looked at current flow and hydrodynamic flow in graphene. You can see here that they put a graphene sample here, they're doing transport, and while they're doing transport, they're trying to actually reconstruct back the J. In fact, this is an advantage of the NV center sensor, because not only can you measure the current, you can actually reconstruct back the J profile, so the current density profile, in fact the full vector profile of this current flow, and that is something that is being very commonly used nowadays. Now, because you have 4 arms of the NV center projection, so you can measure all different projections of the magnetic field, and so from the magnetic field you can reconstruct back the J. inverting the biosavers. Yeah. So these are recent sort of technology applications of using NV centers where people have started looking at faults in chips. So if you have a PCB and you want to investigate if there is a sort of current flow and you want to understand whether the current is really flowing in the way you want it to flow, people have started putting diamond magnetometers sticking on top of those chips and trying to see what is the current flow here. And similarly, some like FPGAs where they decapped it and they looked at the dynamic current flow inside these FPGAs and understanding what is happening to the chips. Another very new recent thing that this is in fact one of the best sort of measurement that they have done is looked at again graphene and trying to see what happens at a very, very localized nanometer scale with very high precision, what is the current flow that is happening in these 2D samples. Okay, now to the biologists, if you are interested not just in chips but in different kind of biological applications, one of the first few examples of applications is looking at muscle twitching. Looking at, this is the first sort of domain, it's still an archive, where they were looking at the cardiac cells and looking at the magnetic signature of cardiac cells. There's another application of C. elegans where they looked at the neuronal signature with NV centers, and here in this again, this is the C. elegans one where they used a nanodiamond in fact and did co-magnetometry and thermometry along with it. Okay, now for the remaining part of my talk, I will focus only on what we do and what is our motivation in this field. So one of the first few motivations that I sort of worked on or is working on right now is a whole sort of a very, very blue sky problem where we want to build a magnetic analog of microscope where we want to look into neuron interactions. So essentially we want to zoom in and focus on one single neuron and see if we can understand how neurons are interacting with each other with these axon potentials and do correlation with the kind of signal and the behavior that we have. So we are of course physicists and engineers, but at the end of the day we take a spherical cow approach and we will say that, well, I have a wire, I have this wire, and so there is current flowing in this wire. So if I have a current flowing in this wire, there is a magnetic field around it. I have a magnetic field sensor. Let me measure the magnetic field and see whether we can actually localize these so sort of signals and see, and then translate it back into the actual image of the neurons and be able to locate this position of the neuron. So that's what we do. We essentially think of these as wires and want to understand the behavior. So for that, we are building a mimic system. So it's a mimic device.
Can I ask a quick question? What is the field strength you expect
I will
measure?
show you.
Okay.
So just in two slides, I will show you what the field strength we expect. Yeah. So this is the kind of imagination I have, where I want to have a slide where essentially we want to build a magnetic field sensor which would be like a helmet, and we would have NV centers everywhere, and what I imagine is that it will pick up the magnetic signatures from these neuronal signals and will be able to detect it. Now in my case, I'm not a biologist, I don't work with cells at all, I work with wires, and that's what the best I can do. We make chips which mimic the behavior of neurons, or even not even neurons, just wires, and just have currents flowing through them and measure and see whether we can make a correlation out of it. So that's what we are planning to do, and that's what we do. So we make chips that look like this, and I'll tell you why we chose this design. So here is our sort of a goal. So we want to understand how to reach this sort of a sensor precision where we will be able to measure these neuronal signals, right? And then understand if we can measure these magnetic fields, can we actually reconstruct back the location of the neuron? How do we do that? Because magnetic field at the end of the day is a vector sum. If you have a sensor, will measure the vector sum of all sorts of magnetic fields around it, right? So how do we locate the position of the source? That's something that we were, trying to understand, and we were very inspired by this paper by John Wicksko, and where they actually look from the magnetic field to actually reconstruct back the current density. So our next sort of work would be to actually make a prototype device, and then hopefully one fine day we will be able to do single neuron imaging. This of course is very far-fetched. Okay, so the first thing we did was we used the very famous cable theory, and this is very well known. We just take this sort of the cable equation, and this is very well known and used to model the neuron and current flowing through the neuron. And except in this case, what we did was we compartmentalized the neuron into small little chunks, and we integrated the current flow in a pyramidal cortical neuron, right? And so what we saw was very interesting. So ultimately you get the magnetic field by looking at the current flow, right? And that is what we are interested, because we want to model what the NVs actually will image, right? What we understand from this is that actually the cell body, which is this axon, the soma, has much higher field than the current that is actually being carried by the wire. So that's very interesting, because you can see from the magnetic field profile, the magnetic field right at a point right below the axon is actually much higher than what happens if it flows through the entire wire, right? So that's very, very interesting, because it's a localized source then. Okay, so we can approximate a complex 3D current flow by localizing the current flow into this axon hillock, and that's what we predicted, and it's about 30 picotesla. Okay, so that's the magnetic field level that we want to work with. Yes?
Yeah, can I ask, just going back, so when you do this reconstruction of the distribution of the current flow, do you have to assume that all 4 positions of nitrogen vacancies is equally distributed? Is that a reality?
That is always the assumption. Yes.
But is that how close it is to your experimentally when you do the nitrogen?
We haven't done the experiment, so I can't tell you.
Okay, but is it generally accepted that you expect?
Yes, it is always expected that you will have
they are equally favorable.
Yes, and that is even experimentally also. Typically, you will always find all 4 classes to be uniform, almost equal. Yes, yes, yeah.
These plots here,
where
have they come from? These on the left, these are from some biological measurements, or?
Yeah, these are actually our simulations. So this is a simulated plot from the cable theory. We calculated the magnetic field by looking at the integrated signal and looking at the net magnetic field, and we observed that this is what we observed, that the axon hillock has the highest amount of magnetic field. Yeah.
I see. Okay.
Can I interrupt at this time?
Very sorry.
This is Professor Dua from London. How can we have the universality of the neurons behaving in a similar fashion when it's almost equivalent to the diversity of the biodiversity of the neurons present on this planet? This can be a single model, but cannot be applied to the full diversity. I don't know. I'm failing to understand.
Can this model be applied to the full diversity of neurons?
Cable theory is very well known to be applied as the standard model to mimic neurons. So this is very well known for all sort of mammalian and non-mammalian sort of.
Mammalian forms only 1.2% of the total diversity. Number one, and number 2 is that in vitro they will behave in a different form. In situ they will go, and in vivo. And the moment you apply any magnetic field, they will change their magnetic conduction. I don't know what the physics part of this one, but as a biologist, I know that part.
What is?
Professor Dua, actually, we are not able to understand the question. It will be good if you can write the question on the text box. Then we can actually get back to it, because I guess as she pointed out already, that this is probably going to be valid for mammalian neurons, but you said that this is going to be very less diverse as compared. So, but let's actually, can you type the question, because the audio is not very clear. So we can come back to it at the end.
Okay.
Is that okay with you?
It's okay for me.
Thank you very much. Yeah.
I'll reframe it up.
Sure. Please do write. Yeah.
Thank you.
Thank you. Yeah. So moving on. So when we looked at all the maps of how the magnetic field profiles actually look like, so it's very interesting. You can see that this is the actual map, let's say, of the Y component. So let's say this component. If you see, it's only a blip that's actually showing that the axon, the cell body is actually having the maximum amount of magnetic field. And this is, you know, I've shown this purposely because this basically shows, and that blown up is actually here, where if you actually saturate the scales, you can see that, you know, as the signal travels down, it splits into two, and you can see the full profile of the magnetic, you know, how the neuronal signal actually propagates down this, you know, through this axon. So essentially this model helped us predict two things. One, that this is magnetic field is kind of high from the cell body, and the second thing is that we can actually use this very nicely to say that the source is almost like a point source, and so we want to see how to, you know, reconstruct back the location of the neurons. Okay, so with that, we sort of moved on and tried to do a predictive model. So we said that if you have a dictionary, suppose you have a whole bunch of neurons, and that is being measured by the NVs. So what you can do is you can build for different time instances what the NVs are going to see. These are the magnetic maps that the NVs are going to see. So for instance, if you have a noisy map that is measured by the, you know, experiment, then what we do is we sort of do you know, a basic, very, very simple matching pursuit algorithm, where we take the dot product for every consecutive 3 time instances or 2 time instances, and we see what is the best possible match. Right? Whenever we find the best possible match with the dictionary, we remove that neuron out. We have located that neuron, and we take it out from and run this algorithm many, many times to figure out what is the actual location of the neuron. And so how well does this algorithm actually works? So we did that, and we said that what we see and observe is that if you have 2 neurons which are separated about, say, 20 microns, and you know, are temporarily, you know, having signals, emitting signals at least, say, 1 millisecond apart, so 2 neurons 10 microns apart with 1 milliseconds of temporal difference between their signals, you can very well locate them. So almost with 80% fidelity, you can very well locate them. And this is one of the simplest possible algorithms. You can really build many, many higher order algorithms where you can. So now the question is that, can we now really do this in, yes?
So how many of these NV diamonds are you talking about? If you have multiple ones, then it should be possible to do a lot better, right?
No, so this is a layer, and let's say we are focusing only on a very small, you know, focal spot.
The layer has a certain density of this.
Yes, layer has a certain density.
And the density is such that they are more than the resolution apart.
Yes.
So then it will not.
That will depend on the sensitivity, right? Because the total net magnetic field is about, say, 30 picotesla or so, and that is also falling with Z.
But so, if I think of it as an array of NV diamonds, and I see a pattern in a sensing of the magnetic field in one, and its neighboring ones, I should be able to locate it much more precisely.
If you have more number of arrays, yes, you will be able to do that. If instead of using one sensor, you have more number of arrays, you will be able to do that.
Okay. Yeah.
Okay. So now how do we do the experiment? So we moved on from biology to a real life experiment. We want to build a setup. So what we do is we have a similar kind of objective. You shine green light, you collect the red light, etc. So we have to stick this diamond onto an antenna because you have to do all the controls. So microwave controls are done through an antenna. So you apply this through an antenna, you stick the diamond on top of this thing. You have a hole here because you want to do the exciting, excitement. So here, so you basically shine the green light through the objective, through the hole of the antenna. So this is actually the antenna. You shine from the back and you see the hole very nicely localized. And then you collect the red light on the same path, or you can collect it from the sides. So this is a bulk diamond, this is a layer diamond, and layer diamond means that the NV is only on the top 1 micron from the surface of the diamond. So that's a very critical part of this image. Okay, to show you some of the pulsed sort of experiments that we can do, you can apply a polarization pulse, you can do the measurement with a microwave, and then you can apply a microwave on, off, etc. And this is the optically detected microwave, measured microwave optically detected resonance that you can see. So just like the cartoon schematic that I showed you, you can see 8 lines. Actually, these are almost merged. You can see 8 lines with 2 splits. So splits are actually corresponding to the N15 hyperfine levels. So here you can see very nicely the hyperfine splitting of the levels. So this is just a standard Rabi experiment. We apply, microwave drives the spins, and you can do a continuous Rabi experiment. You can further do the higher orders sequences like Ramsey. Here you can get about 450 nanoseconds of T2 star. We did, a Hahn echo.
So how are you generating the microwave pulses?
We have an SRS and we amplify the SRS.
Okay.
So this is just a microwave signal generator. Signal generator. Except we have to make sure that the signal generator is very stabilized.
Sure.
And synchronized. These, although they look like blocks, you have to have everything synchronized, otherwise it will not work.
Right. And the power levels typically
we start off with say -5 dBm at the SRS. We amplify it by 43 dB.
Okay. Fine.
They're very high. Yeah, few watts at least. Yeah. So okay, I don't know what happened. Let me see. Sorry, suddenly I went from, yeah. Okay, so we did the Hahn echo, and you can see that you can extend up to 8 microseconds of the T2 star. Yeah. So if you now, instead of doing just a standard sort of ODMR, you can also do a frequency modulated ODMR. And so that just means that we have a modulation of the frequency. And then what we can do is we can apply, instead of using just one, center frequency, we frequency shift key in this case, and we apply this sort of a modulated frequency. And what you can see is actually the instead of seeing the Lorentzian, which is the standard that you would expect, you see actually a derivative of the same. This is exactly the same thing, except we are doing a frequency modulated version of the ODMR. And the key advantage of using any lock-in measurements is that you basically narrow down your measurement bandwidth, and you are mostly sticking to a very small narrow region, and so you're eliminating a whole bunch of noise, and that allows you to improve the sensitivity. Yeah. Okay, so what happens is that if you sit at one location at the center frequency, and if you apply if you have some sort of a modulated magnetic field, you'll see that the field shift, and you can see here with the field on versus field off. And what we predicted here was that you can really get very, very high levels of sensitivity when you have an integrated sensor. In this case, we were just integrating the red fluorescence, the entire bulk red fluorescence. Now, the next thing that we did was that we, instead of using a bulk photodetector, we used a per pixel lock-in detector, which means that just like your CCD cameras have different pixels, in this case our pixels actually are locking detection. So it's an enabled for doing per pixel lock-in detection. And what you can now see is that instead of just the total net signal being lock-in detected, which means frequency modulated, see, every pixel is actually frequency modulated. So here are some examples. So for an entire image, so if you have some location which you're trying to image, you can actually see that each of these pixels are now have the signature of this the ODMR, which is now frequency modulated. Okay, now what does this
mapping to specific
points on the space? Yes, exactly. Just imaging. It's if you have, instead of a photo detector, you have a camera. So yeah, but instead of just collecting the fluorescence, we do lock-in detection. Yeah, so what does this benefit us? That's the sensitivity. Yeah, exactly. What is happening? Why is this going? Oh God. Yeah. So Yes, so this is the sensitivity. You can see that the per pixel sensitivity is actually well below 1 microtesla, and in fact this is something, this is a huge enhancement that we get by using this per pixel lock-in detection. So instead of, so integrated sensitivity is in the picotesla regime, so about 350 picotesla, 400 picotesla, but per pixel, which means each individual pixel will have sensitivity. You can see this is the map of our pixel density, how much sensitivity it has. You can see about most of it is almost, you know, below 1 microtesla per square root hertz, which means that you can actually resolve something in the nanotesla regime. And if you look at, you know, the different kinds of noise, we've done a whole bunch of measurements by seeing what is the best optimal region to work with, by looking at, you know, the modulation frequency, by looking at the noise, by seeing over how much time can we actually do the measurements, and you can see all the, you know, noise statistics that we have obtained from each of this per pixel. So that gives us a pixel analysis of the measurement device, right? So now, coming to the most important part of the measurement, which is if we have a microcoil that is sticking right on top of our NV centers, we want to image the current flowing in this coil, right? And that's where this layer is extremely important. The NV layer is very critical, because if you have an NV layer, then you actually get a very nice and clean magnetic profile, right? Because if you have a bulk sample where your spins are distributed all throughout the sample, you will basically integrate or vector sum up the entire measurement over the entire sample, and that will lose. So that will essentially, you know, you'll see a very blurred image. You will not be able to resolve the image. Yes, the spatial resolution will be lost, and therefore this sample was the most, you know, critically limiting step for our measurements, where we didn't have the sample until last September. So we could not convince the reviewers in the first go that our measurement technique actually works, but they said, well, you have to resolve it and show it to us that this resolution is actually, you know, there in your measurements, and you will be able to see it. Yeah, so we in fact fabricated some gold microcoils. These are 100 nanometers of thick gold microcoils that we place on top of our NV layer, and in fact we glue them, glue the sample. So we started off with just by using, you know, XYZ stages and pressing down onto the diamond. It doesn't work. You have to glue the sample pretty much on top of the diamond, and that glue thickness decides how good your, you know, resolution is going to be. That's unfortunate, but that is how it is. Yeah. So what did we do with it? So in the lab, actually, this is how the entire setup looks like. You have a microscope, you have all the lasers, whole bunch of lasers, you have the equipment around it. And so then we decided that we're going to mimic the neuron, right? So how do we mimic the neuron? It has a bulky head and it has a long tail, right? So this is our bulky head and this is our long tail. So that is what we did. In fact, the first thing when we said was, well, we need what is critical to mimicking the neurons. You have a field which is high and localized at one spot, and then the remaining should be not, you know, fairly in comparison to that localized, you know, sort of spot. You should have the remaining magnetic field to be distributed, and that's what this sort of a design actually mimics. So initially we didn't think that this sort of a design would work, because it's actually very counterintuitive. You think that the currents are actually flowing in the opposite direction and they'll all cancel out, but they don't. So they actually very nicely work very well, and you can see the kind of, you know, magnetic fields that you expect to see in these sort of devices. And we've fabricated these structures with, you know, multi coils to mimic the multi nature of course here this is only 4, we want to expand it. So what did we see? So when we applied a current of about 500 microamps, this is the simulated magnetic field, about 50 microtesla at 500 microamps, and zero standoff means as if the sample was exactly on top of the diamond. Okay, so that's the meaning of standoff. So that's the simulated version. This is what you would see if you were to, you know, look at all the BX, BY, and BZ fields, right? Then what did we measure? Well, when we measured the Z-axis, along the Z-axis. Well, you can very nicely see that it maps out exactly well. When we reconstructed back the magnetic field, it almost looks pretty similar to the simulated fields for the microcoils, right? Because in this case, we can actually reconstruct even from a single axis NV data, we can reconstruct back the fields. So
if you go 10 times down the current, could you recover?
That's the next slide. Okay. Yes, we can actually. Yeah, so not 10 times, but at least 5. I mean, 5, half at least. Yeah, so yeah, what can we do apart from looking at microcoils? You can also look at micromagnets, and we actually fabricated an array of micromagnets, and now we want to actually look at strain tonics, where we want to strain the samples and see the magnetic signatures. And here you can see the very nice sort of dipole signature of of these micromagnets. So you can see how nicely you can see an array of micromagnets being measured, right? So okay, yes, so this is if you have just a simple wire. Now we wanted to see whether we can do temporal dynamics, and this is something that was never done. And what we basically predicted is that because of the sensitivity that this is given by this lock-in measurement, we wanted to see if you can actually do real-time measurements. And in that sense, because typically for a wide field static measurement, it takes about several hours, almost 2 to 3 hours, or if you were scanning, it would take weeks. So if to do those, you essentially, if you want to map in wide field temporally modulated or dynamic fields, then it's very difficult. So that's sort of the motivation, and of course the neuronal signals have their temporal nature. So what we wanted to build was a temporal magnetic field imager. So here you can see we pass a current and we modulate the current, and it's very nicely you can see that this is the signature we obtain from the modulated current. And if you take the Fourier transform of that, you can even see the harmonics very nicely. So, and along with it, the magnetic field profiles of the maps. So this is of course the simulated one. You can see here the contrast is not very good, but as you change the magnetic field, you can very well point out what is the location. Okay. So we took the coil, we did the same measurement, and we even did this at 78 frames per second. Okay, so you can really see that instead of having to measure something for hours, you can here measure something in millisecond time scales. And this was the first demonstration of this work where you can show that, where we've shown that you can actually do temporally, varying magnetic fields in wide field. This is something that has not been done, and you can see also the very nice signature of it in the Fourier domain, as well as you can see the signature of it if you were just looking at the, yeah.
What is changing with time? Modulating
the current, yes, you're modulating the current, yes, correct.
At what frequency?
So this one is about 17 hertz.
Oh, okay.
Yeah. Okay.
But you can then make a movie of this also, right?
Yes, I have. In fact, that is what I'm going to show you. That is exactly what I'm going to show you. So one question that always comes when you show periodic signals is that everybody will say, hey, you did a periodic signal. What about an aperiodic signal? So we actually took a signal that looks almost like our neuronal signal, and we we temporally varied it, and you can see that it actually follows very nicely. And in fact, what is notable here is this is the location which is at the zero when the field is actually changing from positive to negative, and you can see that there is no field at this juncture. So this is it's a change that is happening at the 30 millisecond time scale, and you can very nicely map this on the imager. So, well, this sort of, brought us to the point where we said, okay, well, now we can temporally, measure these magnetic fields. Now is the time to show you a movie where we have multi-coils and we can actually make a movie out of it. See if you can see. Can you see two coils nicely dancing? And if you can now, essentially it means that you can resolve the two coils and signatures from two different locations in a almost real time. And although this is kind of slow, but we want to make it even faster. We are currently limited by SNR and not really the frame rate, because our camera can go much faster than this. This is about 3200 is the frames per second for our camera, but we are at much slower, and that's primarily because we have expanded our microscope to a very wide field, and we are yet locating with almost our spatial resolution here is about 1.7 microns. So we can really spatially resolve but also look at very wide field, but that's only because we have chosen to work with a wide field. Now if I want to go to 250 nanometers, I can do it, which means I can just shrink down and actually focus very tighter and increase the SNR and be able to do it. Yeah, so that's a catch-22 sort of situation, but this should remind you that essentially we can now sort of close the gap between what we started off with, which is essentially to understand what our sensor can do and what is possible. First of all, we started putting together the algorithm to do reconstruction. Then we started putting together the sensor. We started to understand what the temporal dynamics can give us. And then what we want to do is now start moving into directions where we can look at AC wide field. So this is currently in milliseconds time scale. We want to extend it to megahertz. And there is a way to do it. And that's what we are working on, where we want to look into AC wide field sensing. And at the same time, we want to not forget our original goal, which is essentially to do 3D NV center imaging. This is something that has not been done. People do always 2D kind of imaging. You don't do 3D imaging. So we want to do true 3D imaging here with NV centers. And then there's another thing that's going on. Oh God, what is happening? Okay.
Go down. No.
Okay, good. Yes. So we essentially want to move towards mimicked, neuron chips, which are those neuromorphic chips, and that will allow us to probe, systems which are again mimic systems and allow us to investigate and apply these NV centers. Now, to summarize, I want to just point out a few other things that we do in our lab, which is we look at Hamiltonian emulation, which is essentially using the spin qubits Hamiltonian for doing quantum simulations. So you can use any other material which will have a similar Hamiltonian and emulated, and that's what we've been doing. We started looking into some of the problems with emulation, and at the same time we are looking at single NV centers as spin qubits, and looking at spin photon interactions via cavities. So we work with these photonic crystal cavities, and these are fabricated in our IIT BNF nanofabrication facility, where you can see that we've made some cavities, we made pillars, etc., which will allow us to do photon mediated spin photon interactions. And these are silicon vacancy centers. These are in fact at the center are silicon vacancy centers that we've single silicon vacancy centers in fact that we've started probing. And another direction in which we very recently started to probe is trying to create spin defects or even photon defects in 2D materials like HBN. So here we have in fact created some defects in HBN, and we've started to look at their photonic properties. So with that, I have to thank all the people who did all the hard work. Madhur, who has been really the key person, who has built the lab from scratch, piece by piece. Shishir, who's been the next student who's helped him, and then Anuj, who has actually done all the fabrication for all the devices. And then we have a whole bunch of other people around, and maybe sometime I will get to talk about their work as well when the time comes. And of course, without money, there is no hope. So we have to thank all the funding agencies who funded me, and my collaborator, Professor Shaurabh Bandyopadhyay and IIT Bombay, IIT KGP, who is essentially my Madhur's PhD advisor. I have stolen Madhur from him. So yeah, so we've been working on the neuron stuff. So thank you very much for your attention. I'll be happy to take questions.
Thank you very much, Kasturi. It's a very nice talk. So now the talk is open for further questions. Yes, I'll just take first the question at the back. We haven't heard from him, so let's.
So I had a doubt in the spectroscopic data which you showed. So there were some also time domain pulses along with the there was, I think, some sweep in the microwave control frequency, and there was a dips which showed the resonances. Why do you need the time domain pulses for that measurement?
Which time domain pulses? You mean the ones that modulated these?
No, this was, I think, before you talked about the neurons.
Oh, okay. So the pulse sequences.
Yes.
Yeah. Let me see. Let me see if I can go back. This one? These two?
No, this is this.
This
Not
is
this. Before this. This is the Ramsey and Echo.
Yes. Here?
Yes. Here. Yes.
Why do we need this microwave?
So this pulses.
Oh, these PLs. What are these PLs? Or maybe I'll just go over this and you can probably just let me know if that answers your question or what is your exact question. So we have a polarization pulse, which is essentially to polarize the NVs to the ground state, because we need a 0 level to start with, right? So we have to know where our NVs are. So this polarization pulse puts it to that ground state. Then we measure to make sure that we know that we are actually in that to the ground state or not. And then we apply our microwave, which is on resonance with the spin levels. Okay, so 0 minus 1 or 0 plus 1. This is that microwave. Okay, and then we measure again, because we want to know. So suppose you have actually, let me see if I have the block sphere. It's in fact hidden. So if you start off at 0 and then you apply the pi by 2 or pi, and the pi essentially is just driving on the block sphere. So that microwave is essentially just driving on the block sphere. And the polarized, and these pulses are just the green laser that is used to measure the population. So every time you will just project it back and do the measurement. That is what we do. Yeah.
Thank you, Professor, for the nice talk. So I have a naive question. So is there any aging effect of the sensors, like the nitrogen seeping in to the diamond?
No, there is no. This is diamonds are forever. Haven't you heard that? No, there is no aging. No, really. I mean, there is no aging. We haven't seen any decay of the properties of the NV centers or anything, except if oil accumulates on the sample, or there is dust accumulation, the NV coherence time changes, and so all we have to do is do a triacid clean, and that's it. That will bring you back.
So for the fabrication of these sensors, the doping of nitrogen is kind of controlled or something.
That is not in my hands. Okay, this is something where we have to depend on element 6 to actually buy, and in fact, not just element 6, there are few other places who make these diamonds, where essentially what they do is they grow the diamond. So there are two techniques. One is when you're growing the diamond, you introduce the nitrogen, so it will automatically get implanted while the diamond is growing, and then you anneal it, you create the vacancies, so that will allow you to create the NV minus. The other technique is you start off with a very pure crystalline substrate, then you implant nitrogen and anneal, so that will also create a layer. Or if you want bulk, you introduce all the time the nitrogen.
Thanks.
Okay, yeah, that was part of my question. So thanks for answering. Where do you get those? But I have actually two other questions.
Sure.
So you want to have a very high concentration of this nitrogen vacancy. So at what point, or is there any point where you start to worry about interactions between two nitrogen vacancy centers? Is there a
Yes, absolutely.
That's one. And the second is, you were talking about there is some strain sensitivity. So what kind of strain? What kind of strain are we talking about? So that if you can explain it a little bit.
Yeah, so definitely. So for your first question, yes, so when do we have to worry about the interactions? If you have a very high density sample, naturally, if you see the coherence time versus density, there is a sweet spot for density versus coherence time. And there is a calibration that has been done by various people who make these whole bunch of samples, and they have a plot which shows that the coherence time improves, then it actually falls down. So so essentially about 10 to the power of 13 NVs per centimeter cube is a good number for a layer. And if you go more than that, then the coherence time actually starts falling off. And also, of course, depends on the kind of way in which you grow the sample. So whether you do the implantation method or whether you do the delta doping method, it will actually change. Yeah. I'll just answer his strain question. So the strain is what kind of strain, right? So strain is something that is inherent when you have a lattice. You will have natural strain. So now people are trying to see what is the method in which you can eliminate the strain. And in fact, a double quantum sequence can actually eliminate the strain problem. And that is something that came out last year, where you can use a double quantum method, where you use both the +1, -1 levels, and you can eliminate the strain and temperature variations and improve really the sensitivity. Yeah. Yes.
Very nice talk. I had a quick technical question.
Yes.
How thick is your substrate? Because that pertains to how well you can do microscopy in a conventional way.
Oh, so our substrate is currently 500 microns, but the NV is only 1 micron layer. It's only 1 micron.
You have to do epifluorescence, the light has to go through the 500
Yes,
microns.
but you can get one. No, recently we got 100 micron samples.
That would be better.
Yes, exactly. So that's the standard cover slip size. So we have one sample which, in fact, yeah. So we have some samples where you can actually do. So that is the direction in which people are going, where you want really thin samples, membranes almost.
Okay. We have to take some Zoom questions. I think Professor Dua, you want to re-ask your question?
Yes. Good afternoon from London here. Dr. Kasturi, you have mentioned about these magnetostatic bacteria, but I understand that even the dead bacteria also respond to these magnetic fields.
Dead bacteria also.
Okay. Dead bacteria, and every bacteria has its own critical cycle in which the active life is much lesser than the time taken for its being, towards the senescence. How do you account for those dead bacteria coming in your magnetic field?
So the question is, if you are sensing bacteria, for example, so if it's alive or dead, how would you recognize in some sense?
It is likelihood that more than 60 to 70% have taken their life cycle and they are dead, but still responding to the magnetic field. How do you
distinguish that?
How do you distinguish that?
I guess we will have to use statistical methods there, because in fact, we haven't done any live measurement, or neither do I know anybody who has done a case study of live versus dead and seen what kind of difference in the signatures we can get. So yeah, I think we'll have to
see, for a biologist like me and many in Cambridge University, we are yet to use this application at any of the labs or in any of the equipment. So that is why it was little higher.
Looking for an application.
Okay.
Yeah.
I have no idea.
Understand that these dead bacteria, especially that in the neurological system, in neurons, in synapses.
Yeah, anyway, I do not.
I'll pursue this matter further if I get your email address. And
yeah, sure, absolutely. Yes, absolutely.
What is being done in the biophysics department of Cambridge University also, where we are at present. That's all. Thank you very much.
Thank you very much for this pointer.
It was a lecture exclusively for the physicists and not for the biologists.
Okay, thank you, Professor. Thank you for attending and asking the pertinent question. Thank you.
Thank you.
Surajit Datta, you have raised your hand.
Yeah. So may I ask question?
Yes, please.
So can you talk about what is the spin sensitivity you have in terms of Bohr magneton?
Field sensitivity.
No, spin sensitivity.
Spin sensitivity.
In terms of a Bohr magneton.
Yeah, so it is the omega is essentially gamma B here, right? So, and we have our gamma is 2.8 megahertz per Gauss. So that's what we have as the basic calibration sensitivity. And then what we can get integrated is, of course, 350, but you can push it down even more. Yeah.
I have one more question that I have heard this multiple times in different talks, that inverting Biot-Savart's law is not that easy. There is a lot of noise of addition during this invert of Biot-Savart's law if you just measure the magnetic field and convert into a current. So generally people use it in a AC measurement, do you how much noise is addition when you have inverting this?
That is actually a good question, because we are in fact trying to invert our magnetic field to currents and we are not able to do it yet. So we are quite struggling. In fact, with the kind of signals that I showed you here, although we can measure microteslas of field and we can spatially resolve it, we are still not able to recreate back the J, and that's primarily because we are doing this in the temporal way. But if you average for a very long time, and people have shown, like for instance the graphene example, they were able to do it with nanoteslas of field. They can easily reconstruct back the magnetic the J field from in fact inverting the Biot-Savart's law.
Shurajit?
Yeah. So last question to be finished with. So though you have not talked about, so just if you can give me some idea. So when you put your NV center diamond in a front of AFM tip, that so how one can ensure that there is a single spin at the apex of that, or the edges of that tip, that is the crucial, because it is similar like SPM measurement.
Yeah. So actually when people build these tips, so what they do is make these pillars. So from the pillars, you can do what they do is they implant, and then they do a G2 correlation measurement to ensure that you actually get signature of a single photon, and a single photon essentially will only come from a single NV center. So that is how we know that this is there is a single NV center, and from there you attach it to the AFM tip.
But madam, how to ensure that it is the end of the tip? Because that is also crucial for the spatial resolution and the measurement purpose, and how much tip is far away from the sample when you scan it.
So the way they make the tip is with the implantation, they know from the energy what the penetration of the implanted nitrogen is going to be. So typically that is about 10 nanometer. The other, what they then do is they actually etch out the tip to ensure that the NV is actually very close to the surface. So that's how they make in general any bulk sample also. When you need, say, want to do a protein kind of measurement, when you want to do a spin sort of measurement, you have to have the NVs right at the surface, which is about a few nanometers, like 2 nanometers is the best possible reported, where you can get the NV center exactly 2 nanometers from the surface. So that's what they do for even the AFM tips.
Thank you, ma'am. It is a wonderful talk.
Thank you.
Yeah,
thank you.
It was very nice. Thank you. Thank you, Shurajit, for the question. I think we have come to the end of this colloquium. If there are no more questions, let's give a big warm round of applause to Kasturi, who traveled for 2 hours from IIT Bombay to reach here, unfortunately due to construction. But thanks, Kasturi, for coming down, and thank you all in the Zoom audience for being there and also participating in it. For those who are here, we have small snacks outside the West Canteen, so please join us and Kasturi there. Thank you.
Thank you very much. It's really been nice.
And next week we have Basudeb Dasgupta, who is going to give his colloquium on neutrinos. So thank you. Yeah, we can.